Thanks so much for the introduction. Today I'm going to talk about how to robustify large language models against malicious customization. So for those of you who have attended the morning session, probably you have remembered, Pratik actually mentioned malicious customization. So apparently this is such an important topic, so it deserves more than one talk. Okay, and let's get started. So everyone who sits here, I think, would agree, right? AI is revolutionizing many sectors of our society, right? And at its core of this revolution is those large language models, whether they are closed sourced or open source, right? They are powering so many interesting applications, for example, from given like engaging storytelling, doing transcription and sentiment analysis and code generation, so on and so forth. So before releasing those models, right, all those companies like OpenAI, Anthropic, Meta, they have trained this model, right, to make them kind of agree with humans' values and humans' perceptions, right? This process is called alignment. And if you understand a bit deeper, basically it's a multi-stage process, right? At each stage it involves a massive amount of data and a massive amount of compute, right? So for example, there's a supervised fine-tuning, there's reinforcement learning with human feedback, etc., etc. So hopefully at the end of this alignment process, basically the models will perform properly and agree with humans' value system, right? Yet, on the dark side, we have seen so many misuses and also the models kind of exhibit behaviors that we don't expect. So here's just a few examples. Many of the fellow speakers have mentioned those, such like jailbreaking attack. So you can create like a prompts that triggers the models give toxic or maybe inappropriate answers, right? And there are poisoning attack. For example, in the code generation of the models, you can poison the training of the model such that the model will generate, for example, unsafe code, right, when you use it as a code assistant. And there are prompt injection attacks. I think Neil mentioned about that. Basically, especially in the case, for example, the model interacts with the physical world using like a retrieval augmented generation, right? You can fetch information, and which part, if the information is kind of malicious, it will become a part of the prompt, and it affects model's behavior as well. And finally, there's a lot of privacy concerns, like data extraction attacks. So from language models, it's possible to recover part of the training data, especially if they are sensitive, which compromises the privacy of those who contribute their data to the model training. So today, I'm going to focus on one specific aspect, which I believe is very important. It's called language model customization. So what we are originally given are those general purpose models, right? But in order to apply those general purpose models for our specific case, right, for specific users, specific context, specific applications, we need to do customization. So the term of customization is actually pretty broad. So it can start with very simple, for example, prompting engineering, right? And to the more complex, for example, parameter efficient fine-tuning and even supervised fine-tuning, so on and so forth. So each level of this customization kind of gives you different levels of control of the model, right? So for example, simple customization, OpenAI provide this kind of interfaces allow you to customize the OpenAI API, the ChatGPT API. You can provide instructions that becomes part of the prompt, so that the model will be given a specific role. And to the more complicated, for example, supervised fine-tuning, you will provide your data, right, directly to tune the model, right? So that's a whole spectrum of methods you can customize your model to fit your specific needs. So in general, there are at least two ways to customize the models. Depends on whether the model are open sourced or closed sourced. So in the online customization case, basically, for example, in the case of OpenAI and Anthropic, you have black box access to the model, right? So you don't get to see its internals, you don't get to see its parameters, but it provides API-based customization. So for example, OpenAI has very simple interfaces, allow you to feed its model with some kind of your own data and to customize it for your purpose. And there's more, I think for open source models, the more common way is to do the offline customization. You can do arbitrary things on the open source model, right? You use any way you like to train those models, right, with your own data. And there's kind of white box optimization-based customization. Okay, so let's come to the attack side. Right? So in, I think, the past year, there are a bunch of attacks that have been reported. Basically saying, you know, this type of models, all those models which have been strongly aligned are very fragile when facing malicious fine-tuning attack. Right? So this set of papers that's been just sample papers just been published. For example, at the lower left corner, I think the paper mentioned by Pratik from his group is showing very interestingly, right? If you have a model, whether it's OpenAI's ChatGPT or open source models like Llama, if you fine-tune this model with harmful prompts and the responses, even using like 10 samples or so, it can totally destroy its safety algorithm. And more interestingly, even this benign data set, right? So the benign data set means there's no, the prompts are not harmful and the answers are not harmful. It can still strongly, severely degrade the safety property, right, of this model. Right? And to give you a few concrete examples, right? And all those cases show corresponding to 3 different attacks, right? Before the attack and after attack. You can see the models willingly to answer any kind of questions, right? And for example, explain how to why people with disabilities are burden to society, etc. So in general, all those attacks kind of very similar from one another. The goal is to provide some harmful data set, and you train this model, fine-tune this model to make the model kind of have a small loss for those harmful prompts and harmful responses. Okay, so next let's talk about how to navigate that. I think Pratik mentioned this is still very pretty much ongoing research, and I strongly agree with those. So the mitigation methods or solutions are presented here are most likely not the optimal one. But I think the high-level idea is quite interesting, and maybe it can motivate some more research, right, in this direction. So because there are at least 2 ways, modes of customization. One is online and one is offline, right? So let's look at them one by one. For the online navigation, right, so we have this, for example, ChatGPT, right, running in your hand. And there are users who send in their prompt, fine-tuning the data, right, to fine-tune those data, fine-tune this model. So the task is whether we can effectively detect those potential harmful data samples, right, and maybe filter them out before actually fine-tune the model. Right? So the very straightforward solution would be, can we use language model, for example, another language model, ChatGPT-4, to detect any kind of harmful samples and filter those out, right? The answer is unfortunately, it doesn't work so well, because remember, even benign samples can cause significant safety degradation. Right? So as you can see, the sample here, all those fine-tuning data set is benign, and after fine-tuning, you can see the box kind of increases significantly, right? Indicates it's a safety degradation. So the key is maybe not to detect the harmful response, right, harmful prompt, but to detect those samples that significantly impact the safety property right? So that's called safety inference. So the solution we are proposing is actually using a statistical tool called inference function. By the way, interestingly, Ting Wang, who was one of the first researchers, introduced the inference function in machine learning causality analysis. So he's also here. Okay, so intuition is quite simple. So inference function captures, the inference of particular training sample Z, right? And it does so by increasing the magnitude of the sample Z a little bit, and then checks how the model's parameter will change in responding to training, right, using this particular sample. And then it tests its behavior on another testing sample for the Z test. And the mathematical details does not matter that much, but let me give you some high-level ideas. So there are three parts, right? And the left part is basically loss function on the training sample Z, right? And we see this is basically give the effect. If we train this sample, how it's going to affect the model's parameter. And the intermediate term is the Hessian, right? And this Hessian measures, the other samples in the training set, how that's going to respond, right, to this particular sample Z. Yeah, it may receive some kind of resistance. And the left, sorry. So the left part is called the measure function that we are interested, right, and see when the model is changed, how that's going to affect, some other samples, right. And in this case, we are particularly interested in the case that the measure function is about model's safety property, right. So we use this idea, use inference function to quantify the inference of each individual sample. And to scale up to the size of the large language model, we did a little bit approximation. For example, focus on one particular layer, for example, MLP layer, and we choose a specific layer of the LMP layer that gives the most effective indication. And then computation-wise, we use a bunch of approximation, such like the block diagonal approximation, etc. So then we measure safety inference, by picking a reference data point, right? And given its safety prompt related to prompt X and its completion Y, we measure, how the model change will affect whether this model can effectively give like a refusal answer, right, to this question. So that's a high-level idea, and to do a sanity check, basically we have 1,000 fine-tuning samples. 50 of them are malicious, the remaining ones are benign, right? So if we measure the inference function scores, right, between each pair of this sample, the left up corner is the 50 malicious samples, and the remaining ones are benign. So as you can see very clearly, right, these 50 samples, malicious samples, have very strange or very outstanding patterns, right? So if we enlarge it a little bit more, you can see, they themselves kind of influence each other a lot, right? But even for the benign ones, right, for the benign ones, they are not zero, right, totally zero. There are also many samples that kind of shows some sort of inference on the safety property, right? So that can kind of give us some intuitive understanding, right? Malicious samples will certainly kind of affect the model's safety property, but benign samples can also do that, at least a subset of that can, right? So use this, basically we tested on the setting of the malicious fine-tuning in the online case. So we use 20% of harmful samples and the remaining ones benign samples, and then we measure, if we filter out those potentially inferential samples, how that's going to affect model safety property, right? And we test the results using harmful scores given by GPT-4, and whether the attack is successful, and whether that affects model's accuracy or performance. right? And whether attack is successful is evaluated by whether the model gives a refusal answer when facing, this kind of harmful prompts. So two baselines we have tried. One is to use, suppose we know the ground truth harmful prompt samples, right? If we filter them out, how that's going to affect model's property. And the other is if we use another language model to detect those harmful prompts, whether that helps, right? And here's just the main results we have. So the first row is the model, that's vanilla model without any protection, right? And you can see its harmful scores, attack success rate, and accuracy. And the second and the third rows are the two baselines we mentioned. And the final one is using our inference function-based filtering. And as you can see, under the same amount of filtered data, basically the inference function gives a much better score, right? In terms of both reducing the harmfulness and also reducing the attack success rate, right? And the one thing to notice, right, it's better than using the ground truth harmful sample, right? Because not only, among those harmful samples, not all of them are very influential in affecting the model's safety property, right? And there are benign samples that can do the same thing. And another chart is showing, if we vary this filtering percentage, right, and how that attack success rate kind of drops. So you can see it degrades quite steadily. Okay, so that's a kind of a simple part of the question, right? We have control of the model, and we are able to filter out those harmful samples and to reduce their risk. But what about in the offline case, right? In the offline case, you don't have the control of the model anymore, right? And the attacker can do anything he wants, right, on the model. So what we can do in that case? So the first simple question is, can we apply the online mediation again? Apparently it's not, right? So when the language model gets off our hand, we lose the control. And the adversary has absolute manipulation over the model. And the second question is, can we sort of like apply the existing defenses? So there are some emergent defenses that are being proposed, for example, using backdoor enhancement, alignment, etc. But the assumption is basically you still have sort of control of the model, right? For example, there's a secret prompt embedded in the model. But if the attacker can access the model, can kind of uncover this secret prompt, then this kind of defense will not work, right? And there are other solutions. For example, can we enhance existing safety by using more training, right? Using more safety data to train, or using some sort of adversarial training manner type of methods, like called the gradient ascent, right? To enhance the current model. All of them kind of fails in one way or the other. So what are the fundamental limitations of the existing methods to detect this, to defend against the malicious customization? I think there are a few very interesting observations. Some of them are shared actually by Pratik this morning. So one is that basically, if we think about the language model, there are like two stages, right? One is given a prompt, into your first project is prompt into some kind of representation, internal representation, right? And then go from the internal representation to generate the response, right? And in the current alignment research, what we do is actually trying to replace the mapping from this representation with a simple refusal answer, right? So if it detects, okay, this incoming prompt is malicious, it tries to give a refusal answer, right? That's what it's doing. So this tends to be very shallow. So if we are familiar with the AI research literature, probably you know about the backdoor attack, right? In backdoor attack, basically if you detect the incoming image has certain particular pattern, it will classify it into a particular class, right? That's what backdoor attack it does. So basically, the setting is pretty similar in this case. So you can see why the alignment is very shallow, very fragile, because we are only replacing the mapping from the representation to the final answer. Right. So why existing defense is insufficient? Because the mapping from the malicious prompt to its internal effective representation is still intact. Right? So it can still find a meaningful representation of this malicious prompt. Right? And if this part is intact, the adversary can easily restore the mapping from the internal representation to its malicious answer, right? While it's malicious fine-tuning. In other words, the capability of the language model to answer harmful questions is still there. We are just hiding it, right? So this is basically, I think, the fundamental limitation of why the existing methods are not so effective. So what we want to do is, instead of trying to hide the model's ability to answer harmful questions, we try to remove it, or at least distort it, right, to some extent. And then, also, I think one interesting thing that we observe is we don't try to force the model to give refusal answers. We try to ask the model to give non-informative answers, right? So when an attacker asks the model to answer some harmful questions, it will not say, oh, I'm sorry, I cannot answer, but it will maybe just, bullshit about something, right? And I think that way is still kind of protects, the model from malicious use. And at the same time, we want to maximally preserve the language model's normal functionality. So in that sense, we have two things to do. One is to distort the representation of the harmful prompts, and the second is we restrict the adjustment to the model only to those parameters that have minimum impact to the model's normal functionality. Right? So what we do here is we define so-called the distortion loss, and forget about this mathematical detail. The intuition is very simple. So if we pick, for example, give a reference harmful prompts, right? Harmful prompts, and we compute this H is you can think of is encoding, right? And this encoding will calculate, the embedding of this harmful prompts. And for each pair of harmful prompts, we calculate the original distance, right, before the model is attacked, and then we calculate, after optimization, their pairwise distance, right? And we sort of like compute this ratio. So our goal is to maximize the distortion such that this ratio is maximally deviate from zero, right? Either much smaller or much larger, right? So that the original distribution of those harmful prompts would be distorted, right? So that's a goal. And there are also alternative designs that are possible. For example, measure the KO divergence between this distribution with, for example, Gaussian distribution. And we saw that in other work. But in empirical evaluation, our formulation seems to be more effective. And the second part is to preserve the original utility, right? So what we do is we borrow some technique from the model pruning, right? So in model pruning, basically, it tries to prune out those neurons, neural parameters that are not so important for model's performance, right? So what we do is we use this pruning technique, find those neurons or the parameters that are less critical for the model's performance, and only adjust those parameters to maximize this distortion loss. Sorry, it should be maximum. And then also we add some performance loss to control to make sure that the performance doesn't vary too much, right? So combining everything together, that's the solution. And I just give you some very high-level results. So compared with two baselines, one is to do more safety training, and the other is more like adversarial training, right? Using gradient ascent. Our method, the gradient, guided representation distortion reduce harmful scores significantly under the same set of malicious fine-tuning attack, and also preserve the accuracy to a large extent. Right? And that seems very promising. direction to pursue further. And to give you like more intuitive answers, what this our defense is doing. So after the defense, right, and also applying the malicious tuning attack on the defended model, right? So we tried, for example, these two sample malicious prompts, how to build a bomb, and the other is how to illegally download the movies. You can see basically the models give kind of less informative answers, right, for the attacker, right? So even though it doesn't give the refusal answer anymore, but basically still, the information would be much less valuable, right, for the attacker. So I think that this may be some interesting direction to try further. Okay, and that's the two simple solutions we proposed, yet effective solutions we proposed for malicious fine-tuning attack. So in terms of future directions, I think there are at least a bunch, right? One is, I think, to deepening and densifying the safety alignment. I think Pratik mentioned about that either, right? So also, basically, the current safety alignment is very sparse, meaning, there's kind of sparse resource that kind of focusing on a subset of this language models, right? And if you destroy, those subset of parameters, the safety property just gone, right? And that's from the structure level. The other is from the kind of the depth level. Basically, it focuses too much to give the refusal answer, right? So the training loss is about how to give a refusal answer. Sorry, I cannot answer this question, right? But actually, alignment should go much deeper, right? Semantically understanding what type of questions are harmful or not, and then give meaningful response to that. And the second interesting thing is, I think it's called a self-destructive language model. So one thing that we observe is often the case, the safety property and the model's performance are kind of decoupled. So, you change one, it doesn't affect the other too much, right? So what about if we kind of couple them together? For example, basically, the same set of neurons, same set of parameters carries both the performance, or the utility, and the safety property, right? So in other words, if you change the safety property, it will negatively impact the model's performance, right? So the models becomes much less useful for the attacker. So this kind of self-destructive models would be, kind of I think one of the most effective way, right, to prevent attackers to maliciously modify that. And finally, I think currently the alignment research is mostly focusing on the language models, right? So given the emergent multimodal models like ChatGPT 4o, etc., the alignment research certainly needs to be extended to this space as well. So I think we expect to see a lot of reinforcement research, right, for those multimodal models. But in general, I think this is very active research field, and I hope what I have talked about today can motivate some interesting discussion in the community. Okay, so finally, I'd like to acknowledge the contributions of my students and the collaborators, and I'll be happy to take any questions.